This is going to be an amazing talk, so I'm really glad you're all here. Just a couple of quick notes as we head into the afternoon's agenda. You'll see QR codes come up on the last slide of the speaker if you want to give some feedback. Capture that. There'll be a little quick survey. They're also going to send one out by email to all attendees towards the end of the day, so you can rate the overall event and give us some awesome feedback. You'll see some great sessions up here throughout the afternoon, as well as back downstairs where the keynote was. So just take a look at those agendas and pick some great sessions to be in on. There'll be a coffee break mid-afternoon as well, and then ultimately a reception at the end of the day. It is my pleasure now to welcome to the stage Ken White. Ken is a security engineer whose work focuses on networks and global systems. He currently leads applied encryption engineering in MongoDB's global product group as security principal. Ken is co-founder and director of the Open Crypto Audit Project and led formal security reviews on TrueCrypt and OpenSSL. He currently serves on the Black Hat Security Conference Review Board, leading the cloud and platform security tracks. He tweets about biscuits, his dogs, good curry, and sometimes security at Ken White, 2 N's. Please give a warm welcome to Ken White.
Thank you. Appreciate it. All right. Well, let's dive in. Let's talk about the trust problem, particularly in the cloud. So I have a sensitive application. I've got user information, I've got contact information, maybe credit card data, maybe billing data, PII. Where can plain text get exposed? That is, where in a system, if you're thinking from an architecture perspective, where can sensitive data potentially be at risk, right? So the most obvious thing is somewhere between where your web service or application sits, or frankly, where your end user sits, over the network to the database, right? The second is, in the context of a database, there's physical files somewhere, and those live on disks. Maybe they're cloud storage, maybe they're local NVMe volumes or SSD volumes, but in any event, there's physical files that underlie a database, right? So what about those? Well, it's sort of standard in modern applications, right? So in transit, we think about that, and on disk at rest, we think about that. So we traditionally use something like TLS or HTTPS for network encryption, and that does a pretty decent job in terms of intercept or surveillance from point to point. In terms of the disk encryption or on disk, depending on whether we're talking about the cloud context or a data center, where you're managing your own systems, typically volume encryption is enabled. I mean, on most desktops, it's a single click, right? When you first install the application, it's pretty straightforward. With MongoDB, on Atlas, for example, in the managed database service, we use encryption at rest just by default. You can't disable it. So every cluster that you start up, even if it's like the most toy basic sandbox kind of free instance in the developer tier, there's 3 underlying VMs that get spun up, and each of those have volume encryption. So that entire disk is encrypted. In Atlas, you can also say, well, I want to have a little more tight control over data lifecycle governance. So I'm going to use my own keys. I'm going to create a really narrowly scoped identity role. I'm going to delegate that either in a traditional service account or preferably in a user assumed role. I'm going to delegate that to the service, and then you can encrypt not just the whole disk, but the actual individual MongoDB data files that underlie that. And that's called the encrypted storage engine. And those are really important controls, and they are very helpful parts of the application. But a lot of times, I think the mental model for what these do isn't really well developed. At-rest encryption helps you when your database is not running, right? You say that again. When your database is stopped, at-rest encryption helps you. If you're worried about a disk being, retired in the data center, you're worried about potentially another, tenant in a cloud service somehow having access to, say, a snapshot or, an EBS volume snapshot or something like that, it helps. But none of those address a database that's up and running, which most databases are always up and running, and none of those address what happens to an application user or a DBA or anyone else who's actually accessing the database. What I mean by that, when you're using a DB, data that are being operated for queries, for updates, for inserts, for all those sort of traditional lifecycle applications, they're in use. They're clear text in memory in the database. What does that mean? It means potentially, well, let's say we've got a decent job with modern TLS protocols or modern HTTPS in the case of a service endpoint that's accessing the system. So we've dealt with the network side. We've got pretty decent storage encryption, but what's actually vulnerable? This turns out to be really important when you've got things like PII, when you've got things like billing information, when you've got things like medical records or other sort of traditionally sensitive applications, right? DBAs. Obviously, DBAs need to be able to do things like look at patch levels and do security updates, maybe assign roles and user management, things like that. And if you're managing your own systems, you would need to be able to do updates, you need to be able to do backups and things. But do people who have those job responsibilities, do they also need to see that in your HR record, your routing number to your bank account is X? Do they also need to see the actual social security number or mobile phone numbers or things in the databases, the applications that they're managing? And often the answer is no, and so it'd be nice if you could sort of separate those. The problem is DBAs have access to everything, right? If you're a global cluster admin, you can kind of see anything. There's another element too, though, which is how about the service provider? What if someone gets root access on the machine, on the actual VM that's running the database? What if someone is able to inspect processes while things are running, right? None of those other controls deal with that. Sort of the assumption is, well, why would you access data unless you used like a database connection? Well, if the data were really valuable, you know, there's lots of reasons why someone would be motivated to do that. So is there a way to protect data that's in use? Is there a way to protect that data that's in memory? Well, there is. So back in July, we introduced a feature called Queryable Encryption. I'll kind of go through the basic flow here. Let's say you have a healthcare application, right? And you have an authorized user. They're sitting at the app side. The developer has written in the application code, DB billing find, and then this social security number. With Queryable Encryption, and previously client-side field-level encryption, what happens is the drivers will look at that and they'll say, oh, okay, well, this data has been tagged as encrypted. I need a key to decrypt it. I got the key in cache, you know, in memory on the application side? If the answer is no, I'm going to go up to a key provider. I'm going to pull that down. And then what I'm actually going to do is send a special search token to the database. So from the database's perspective, it's not being asked to find SSN, you know, 901.10.4312. It's being asked to find something else. It sees that. It goes through a step of procedures we'll go into in just a second. And in this case, let's say there's 3 entries in the database with that social security number. Look at the SSNs on this display. So they're actually encrypted 3 different ways. So I've got 3 records, same person, same social security number, but they're encrypted differently. Database says, I don't know what you asked for. I don't know why you asked for it. I'm not even sure what fields you're getting, but here you go. Here's a bunch of encrypted records. It goes back to the driver. The driver says, oh, well, this is an encrypted database. I'm going to automatically decrypt that and then hand it back to the application. So again, the developer wrote DB billing find, and the record they got back was the regular plain text. It's really nice. They didn't have to think about the encryption. They didn't have to think about doing that translation. So in this model, encrypted fields are always stored, they're transmitted, they're processed, even if something happened to HTTPS or TLS, in the case of the direct DB connection, even if something happened to the disk, those data are still protected, including queries. So even in the query log, we don't know what was asked. We only know the encrypted search tokens and things that were constructed. This is a view from Compass. This is a person who has global cluster admin privileges. on this database. So they can create roles, they can drop the database, they can do all kinds of interesting, creative, destructive things. What they can't do is they can't access those sensitive records. Because unless they have a username, some kind of identity, whether it's LDAP or IAM integration or federated identity, whatever, they still, if they don't hold the application keys, those end-to-end encryption keys, this is what they get. Now, Compass happens to display it with asterisks. If you dig into that, it's just a binary data field with ciphertext. Now, if someone has the proper privileges to connect and be able to see these collections, but they also have the application key, Compass will see that because it's been pre-configured with your key, and this is what's displayed. And you can actually, in Compass now, it's kind of cool, you can toggle between these two modes to sort of look at what the views would look like if you didn't have that access. This is a dummy record. As part of the exercise of going to building like 10 and 15 million record databases, we had to get kind of creative. But anyway, that gives you a sense of it. So what is the security model exactly? What we call this is a multi-snapshot security adversary. The idea is that either a DBA or a sysadmin at any point in time can take a copy of everything that's in memory, everything that's on the disk, the query logs, even if they had, I'm not sure if people are familiar, but there's VMware's had this for a long time. GCP has something like this. I don't know if Amazon does natively. There's something called, it's like VM motion, but basically you move a live running VM from one physical machine to another. Now, at some level, it's fairly straightforward to get your head around because it's like, oh, we would just take a snapshot of the disk, put it from here to there, do it really quickly, and then, and then move everything over here. What's different, though, is they actually do snapshots of memory and make that live so that you don't lose more than, a couple of network retries of an active running system. Well, that's interesting because it means somewhere over the network, we're also transporting a memory snapshot of this potentially sensitive database. Oh, sorry, and then also, even L1 through L3 cache on the CPU. So this is the sort of level of confidentiality controls that are in place with the security model. The formal security guarantees work like this. In client-side field-level encryption, what we did is you have a document, the fields are encrypted, they're put in the database, and that's kind of it. Your regular user collection, whatever the database collection is you're using for your app, it basically looks the same thing. There's a little bit of metadata inside those encrypted fields, but otherwise, to all the tools and things, it just looks like a normal collection. In this case, with Queryable Encryption, we do a step further. So you still have the protection of the document that's got strong AES protection. The difference is we're also building some encrypted indexes, and I'll show you what that looks like in just a second. The mechanics, if you're in a regulated environment, you may care about this in terms of FIPS. This is not a new kind of crypto. We're not rebuilding primitives. If you use OpenSSL that's FIPS approved, if you're using Amazon Linux, if you're using Windows that's got a FIPS authorized module in the OS, we just call out to the underlying operating system. So we sort of inherit that. If there's a bug or something in the core crypto library, you just update your application OS and then you're done. You don't have to do anything special. But that's really important because there are a lot of environments where you've got sensitive systems like this where systems have to be kind of qualified, right? They have to be sort of really carefully vetted and approved. Just some more mechanics. There's a 96-byte composite key. Some are used for the message encryption, the actual document. Some are used for HMAC for integrity, so that if an attacker goes in and sort of manipulates things or like modifies one bit at a time to try to create what we refer to as an encryption oracle, there's no, they don't get any benefit by that. It's tamper resistant and misuse resistant. But lastly, this last bit is important too. There's a separate key for encrypted search. The key management. So there's field keys. You can, right now, create them manually if you want. You could have like an SSN key, a mobile phone number key, a billing, account balance key, something like that. But the data, and those are stored in the collection, but they're stored encrypted. So essentially, if you trust AES to protect your data, you should trust it to protect your keys as well. We use those in the, in the cluster where you're accessing in a way that it never sees the clear text of those keys, right? You never share the keys. There's no mechanism for you to share or for the keys to traverse this sort of network boundary. The backing key management is pretty standard. All the major hyperscalers are supported, so natively AWS's KMS, Google's Cloud KMS. If you've got an HSM appliance that speaks KMIP, if you like HashiCorp, or even if you wanted to use your own secrets manager or custom key service, that works as well. So that's all kind of standard, but what's interesting about this is it's not just doing a point, what do we call it, a match expression on give me this social, give me this credit card number. What if you were able, on encrypted data, to be able to say, no, I just want the final 4 digits of a social security number, or the first few letters of a name, or somewhere in a comment field, the word slow or angry, or or some other kind of substring that's meaningful, in a way that the database still has no idea what you're asking, and on completely randomized data. So this is a really innovative sort of advance in the field. A couple of the mechanics around, or the design constraints around this, the client has to be stateless. It turns out that Java, C#.NET, Go, Python, and real-world networks die a lot. And they die in weird ways. They die partially. You have network sessions that are in paralyzed mode, where you've got sort of the equivalent of the old school connection pooling, where you kind of get a flaky connection that sometimes connects, sometimes doesn't, sometimes dies partway through a transaction. Sometimes networks just partition and you can't, one primary can't talk to its replica set members. So, these are some real world constraints. There had been work in the academic literature for like 15 years around this technique called structured encryption. I think most people, when you think about database encryption, you may have read like in the tech media, things like homomorphic encryption, maybe differential privacy, maybe oblivious RAM, things of this sort. And each of those have their applications and their use cases. But it turns out if you want really high performance search on randomized data that have a minimal leakage profile, it's really hard. Structured encryption is one technique that's been being developed for 15 plus years in the academic world. Lots of cryptanalysis, lots of improvements, lots of innovations, but it just hasn't been heard much about in sort of the commercial world. It fundamentally has, as I said, the encrypted document, and then these structures that are called encrypted multi-maps. Those let us do things like range searches, substring searches, things like that. I'll get into it in just a second, some more of the details. Fundamentally, one of the key design requirements was we can't have a 10-second query, right? We can't have a lot of chatter back and forth from what was normally a sort of a get and respond kind of loop, right? We can't have searches that slow down linearly like homomorphic encryption and other types of things do, right? That's just not realistic. We need on 10, 20, 100 million document record sets, millisecond level speeds, and that's what we built. I mentioned some of these, the partially or fully homomorphic encryption. Those are really, they're cool techniques, but they have, but they're purpose built. They're meant, in the case of FHE, for example, for arithmetic operations. They do a great job with certain, shared models where you need to look at sums or statistical means, things like that. They're not so great in practice for general purpose database query. Secure enclaves, the jury's still out in terms of some of the security guarantees, and secure enclaves are an important part of the application stack in our view. But fundamentally what they're doing is, at some point in that, you're handing clear text data that's running in a protected hardware component, which may be by virtue of being proprietary, not a lot of information. There may not be a lot of attack vectors, things like that. But if you have to, either for regulatory reasons or just straight up defensive ops, have a system where you cannot have any possibility of the database administrator or the database service provider that can see clear text sensitive data, then your choices are basically end-to-end encryption for high performance. Some of you may be familiar with client-side field level encryption. Just to say, it's not being deprecated. CSFLE is incredibly performant. It's also native, and it works with all of our standard tools and things. Queryable encryption is in public preview now. It's really meant for net new. It would be possible, but probably not an easy thing to migrate an existing application to Queryable encryption. Just some of the other differences. They both have, actually there are no differences here. I need to take this slide out. I think we brought this over from World where a couple of these we weren't certain yet, but anyway, these are the similarities. The key thing is for overhead, if you're really, really constrained on storage, FLE is going to make the most sense because it basically adds like 2% to your storage and it just works. The downside is it's limited to direct equality matches. This social security number, this mobile number, this date of birth. But if you want to do more expressive, more rich queries, queryable encryption is something you might want to consider. If your application is read heavy, which most are, or if it's like 90 reads, 10% writes, it might be a good fit. If your applications do hundreds of millions of batch inserts, probably not a great fit. It is highly optimized for fines, and there's a fair impact on both storage and performance for writes. One thing I want to say real quickly about this, when we built client-side field level encryption, we worked with 3 different teams of academics around the world. And one of the teams was the Encrypted Systems Lab at Brown University. These 2 people, Cindy Kamara and Tariq Mohaddad, they were really helpful in letting us think through what are the guarantees we can provide and what are the things that we don't guarantee. Like what are the sort of more nuanced parts of our security model. And they also helped us kind of audit the code and think through some of the early design. That partnership was really, really, it was fantastic. And we benefited tremendously from it. So through a series of conversations, Senny, who led that lab, kind of pioneered the entire field of structured encryption like 15 years ago. We were fortunate enough to be able to acquire their spinoff, their commercial startup from the Encrypted Systems Lab. And so now about 2 years ago, Oroki Systems is now part of MongoDB. And we have developed, well, let me put it this way, we have made a major strategic investment in security. And I think we have, as of this month, 5 full-time PhD cryptographers. So a really serious investment in sort of next-gen and applied crypto. So we're super excited about that. Again, some of the trade-offs, performance, reads are very fast. In some of our testing, we're seeing 1 to 45, 50 millisecond speeds on 5, 10, 15 million document data sets. The evaluation is still sort of ongoing. If low volume, if you're doing like a few hundred at a time on writes, it's fairly negligible in terms of clock, wall clock kind of performance. If you're doing massive batch updates and inserts, there's a pretty heavy tax on the throughput. We have not yet built in insert many, and so that's in the very near roadmap. But as you can imagine, being able to batch insert, say, 100 documents at a time is going to have, in our view, a really nice performance benefit. To give you a sense of this, so in a test example, I think we had, 15 or 20 fields, maybe 6 or 7 encrypted fields. That was weird. There was let's say a 6.3 gigabyte user collection. It's about 5 times that for the search indexes. We built a couple utilities to do compression. We're going to be automating that, so it's not something you have to think about or deal with. And generally speaking, you don't have to if you're not too concerned about space. If you're really constrained on space, or you're thinking multi 100 million record data sets, then there's some techniques called compaction that may be useful. So what's in public preview? The core framework. This is all open source. It's on GitHub. The equality matches. Compass and Shell are now shipping with Queryable Encryption. It's literally a button click to enable. You give either a local key or your KMS, your IAM credentials, and it just works. We started this with a 6.0 release in, I think, late July. So this is for evaluation, but we've already seen some of our biggest strategic customers do really deep evaluations and hands-on. A lot of excitement about it, lots of interesting use cases. The focus is on feedback. We do not recommend using this in production. We almost certainly will do breaking changes. The additional queries coming, as I said, range and substring. How can you try it out? It's on the downloads page. If you want to get into the details of some of the drivers and the mechanics, some more information there. In all of our major supported languages, I think Ruby may be a little bit delayed, maybe for another month with all the current stuff, but otherwise, all of our current drivers are shipping with it. Every OS under the sun, including CentOS on PPC and CentOS on IBM Z series, if that's your thing. Couple last things on key management, which are really cool. We got requests from folks that once they create an application with Queryable Encryption or client-side field-level encryption, sometimes they want to move to, say, a different Amazon account or into an HSM or from an HSM, and now it's a single API call. So you can say, move my keys from this local developer instance to KMS, or move from this KMS account to that KMS. Or, and this is really cool, move from KMS on Amazon to Google's Cloud KMS with a single API call. Yep, and you don't have to decrypt and re-encrypt all your data. It's seamless, there's no downtime. Yep, every combination of local and the 3 hyperscalers and HSMs you can do in that migration. Oh, and I don't know if this would apply to a lot of folks here, but we do work with some users that are in really sensitive financial regulatory environments where they can't use sort of standard randomization seeds on OS. So they need to use like a hardware module to generate entropy. So if you want, you can actually use that and bring your own seed material for the systems. And we'll stop there. I think we have a couple minutes for questions if there are any. Otherwise, I'm happy to do some demos later and I'll be around. Go ahead.
I see a question back here.
So you mentioned all the drivers, like Node.js drivers, going to be updated. Is there going to be any changes in terms of like if our application is already written all of the queries and all of that, if we wanted to switch over to encrypted queries? Do you anticipate any code changes on our part to take advantage of?
So there's some things that that you'll just never be able to do, right? There's certain things that either leak information or in order for the database to do it, it would have to have access to the clear text, which is sort of the whole point. So there's certain aggregation pipeline operations, things like sorts, you're gonna have to sort client side, because if you sorted on the database side, you'd be leaking a lot of information about frequencies and orders and things like that. You can imagine, if a simple case, you had a states table, right? If they're done alphabetically. So if you're talking about equality matches, in general, no. So these are top level and subdocument fields are supported. You can encrypt entire subdocuments as well as individual fields. In terms of code changes, I'd say this for Queryable Encryption specifically, but including client side, you do want to have kind of a data review to make sure. So here's another example. Let's say you wanted to ask the database, give me all transactions that occurred in this geolocation plus 5 miles around it. It can't do that. A, it doesn't know what the location is that you're specifying because it's encrypted. B, it doesn't know what those others are. And so, there's certain things that if the database would have to know it to do the operation, that it can't. But for the vast majority of CRUD operations in a web app, you're probably in pretty good shape.
We have time for one more. Thanks, Ken.
Yep.
You mentioned that you can specify which fields you want to encrypt.
Right.
Is there any way you can encrypt partially the information on a field? For example, Social Security, if you want to be able to see the 4 last digits of it and not the rest of it.
So the question is, can we encrypt part of the field, like a part of the Social Security number, like the last 4 fields, 4 digits, for example? The MongoDB has lots of redaction capabilities. In fact, there's a whole chapter in Paul Doan's book around doing redaction. You can, when the substring search ships, you'll be able to search on those. But in terms of partially encrypting, now you'd have to, at the application level, split that. And then the concern would be, well, now your space just went from, I don't know how many billion in the security range to 10,000, right? So some of these trade-offs you've got to look at, but no, there's not a straightforward way to do partial encryption. What I will say is that a lot of the commercial techniques to do partial redaction or tokenization, if you dig even this least bit sort of past the surface, they're really limited security guarantees. And maybe that's a trade-off you're willing to make, but a lot of times with tokenization, you have an incredibly sensitive database, an application, and the answer is, well, we're going to put this tokenization thing in, which knows both the ciphertext and the clear text, and now you've got to defend 3 different pieces. So it just requires kind of intentional thought, as you look at these for sensitive workloads. Right.
Awesome. Please, Ken, will you be around for questions?
Absolutely.
All right,
Yep.
So you can find Ken. Please remember to scan the code here to provide some feedback and rate the session. Please give a warm round of applause for an awesome talk from Ken White. Thanks, Ken. All right, we're going to take a brief break here, and we'll be back for another awesome session in about 10 minutes. Thank you.